have the opportunity to present our latest product on the interferometric radar family that is a radar for critical monitoring, and its name is RockSpot. RockSpot has been pushed into the market in 2020 in the middle of Italy lockdown for COVID, and during the last year it has been adopted by several open pit mining companies. So first of all, I want to show you what we are going to see during this presentation. The first point is the motivation. Why we have developed this kind of problem, and what are the problems we want to solve for our customers. And then I'll show you how the system is composed. And I'll give you some details on the hardware part of the system. After this, we'll jump on the theory, something very easy, don't be scared, but I'd like to give you an idea of what the radar is capable to measure and how it can be possible. After showing you some basic performances, we'll go through the key features of the product, and I'll show you how the monitoring session can be set up, and what is possible to see with the GeoCloud platform. And in the end, maybe the nicest part is the case. I'll show you some real case that we have collected during the last year. So I would like to start talking about which kind of geo-events are the ones defined to be critical from a monitoring point of view. We are talking about all the geological events that have a sudden falling of rocks, snow, mud, debris, and related to geological and environmental hazards. Rockfall, of course, are a major hazard both for open pit mining and mountains region or coastal cliffs. And also avalanches are frequent and damaging in mountains regions. In general, they all have one thing in common. They are characterized by short time precursor, and sometimes they don't have them at all, and the fast collapse. They happen in few seconds and are a potential huge hazard. So here I reported very schematically the common behavior of a rockfall events versus a progressive slope failure. On the x-axis, there is the time. On the y there is the deformation in terms of measured displacement. The main differences between a standard slope failure and a rockfall is this yellow line that represents the deformation before failure, that is very small or not even present in the case of rockfalls. Instead, it is an evident transient in the standard slope failure. The evolution from the stable phase to the critical one is very quick, and rock can fall with a velocity of meters per second, and moreover, the sudden falling makes it difficult to have a real-time warning. Looking at the current technology of the interferometric radar, like in our family, IDS, Hydra, ArcSAR, and all the other interferometric radar that are on the market, we are able to measure very small movements that can be a precursor of rock or of a rockfall, and the maximum velocity measurable is very slow. We are talking about centimeters per hour. So this kind of radars measure only the small deformation before the event, if any, but not the event itself. That's why we have tried to fill this technological gap existing between the interferometric radars that, again, measure the small deformation before the event, but they are not able to detect the event itself in real time, and the laser scanner that can perform volumetric calculation after the event. That's why we have developed a radar that is able to detect, track, and alert while the event is occurring. And this product is the RockSpot radar. So after this brief introduction, we can have a look to the system architecture of the RockSpot radar on the hardware components of the radar. So a question, what is the basic feature of RockSpot radar? If I had to recap in a short statement, the main feature of the RockSpot radar, I think it could be a radar able to locate, track, and alert on rockfalls and avalanches in real time. So 4 keywords: locate, track, alert, and real time. These simple statements give us a picture of what the radar is capable to do. And here I'll show you a graphical representation of this statement. Very simple. There's a slope in front of our RockSpot radar. RockSpot provides continuous monitoring, and suddenly a rock falls down from the slope. RockSpot is able to trigger, after 1 or 2 seconds, both local alerts, such as a bar to close the road, a siren to advise some workers, a traffic light, etc., and notifications such as mail, SMS, and pop-up, both in the acquisition software, that is the controller software, and in the GeoCloud platform. We will see later these 2 kinds of software. The system is made of 2 hardware components: the RockSpot unit, that is called also the survey unit, and the control unit. And we have also 2 kinds of softwares: the controller software, that is the software on board of the radar, and its purpose is to have a control on the hardware part. And it is also the interface where the user can easily set up alarms, notifications, etc. And then there is the GeoCloud platform that could be on-premise and on cloud, and can collect the data of multi-site or multi-units. And it is a sort of dashboard where the user can have a look to the events that have been triggered and perform back analysis, statistics, etc. Looking in more detail the other part, the control unit is this one. Is an electric panel that gives power and supply to the survey unit, and up to 4 security output devices, like the bars, the traffic lights, etc. Inside the control unit, there is also an industrial PC on which runs the controller software and the offline processing. Just a brief introduction on the processing. We have 2 different kinds of processing. The real-time processing that runs on the radar, on board of the radar, and it provides the real time. So after 1 or 2 seconds after the detachment of the rocks, this processing is able to give an alert. Then we have the offline processing. The offline processing is something that enriches the information of the events. So offline, we can add information about the maximum velocity, the area interested by the event, the trajectory of the event. So all these more detailed information have been made by the offline processing. Okay, so let's come back to the control unit. On the control unit, the user can access to this PC remotely via remote desktop or via tablet. And the control unit is also equipped with an antenna for 4G and Wi-Fi. And there are also 2 battery packs for battery backup. control unit is also weight about 30 kilos. So it is very easy to mount on a pole, on a wall, by only one person. So it's COVID compliant for social distances. Only one person can mount it. The survey unit is the acquisition unit and processing unit, the real-time processing unit. Into this shell, there are the radar unit, the camera that provides the real-time streaming of the scenario and record the event when it occurs, the GNS for the automatic georeferencing, and the module for the real-time processing. And also the survey unit is very easy to fix to the pole or to a wall, but only by one person. The installation for this kind of hardware takes about 20 minutes, half an hour maximum. So it's very easy. So once we have clear the main components of the system, I think that we can go through a quick overview of the physical principles underneath rock spot radar. So rock spot radar uses, in principle, three techniques: frequency modulated continuous wave radar technique, interferometry, and Doppler. So the FMCW technique is able to determine the distance of the rock from the radar, that is the range. So the range is the distance between the radar and the rock that is falling down. The distance is measured by transmitting a frequency modulated signal and comparing it with the signal back reflected by the target. This kind of radar can distinguish in distance more than one object at the same time. And so this capability is expressed in terms of the distance resolution. So radar FMCW to determine the range. The interferometric technique is another radar technique which determines the object angular position by comparing this time the phases of the signals received from multiple independent antenna separated by a certain distance. This is possible because into the survey unit we have more than one antenna, so we can do interferometry. Doppler technique is a particular radar technique. Maybe you are familiar with the Doppler effect. It's the same. The presence of moving object is determined by the comparison of the received radio frequency with the transmitted ones. So a shift in the received frequencies with respect to those transmitted indicates that something is moving in the scenario. So by processing this information, so range, angular position, and velocity coming from FMCW, interferometry, and Doppler, it is possible to provide alarms as soon as detected object has been identified as falling rock or any other fast-moving geohazard event. So I think that the pretty new concept here maybe could be the Doppler. So let's dive right into the definition of Doppler radar. What does it mean? If we have a radar, a rock spot radar in front of the slope, this radar is continuously transmitting. If everything on the slope that is monitoring is at rest and nothing is moving, the transmitted frequency and the reflected frequency are the same. And the radar that continuously transmit and receive radar signals will not trigger any alarm. On the contrary, if something starts to move towards the radar, the reflected frequency increases. And from this variation of frequency, we can determine the velocity of the moving target. The maximum velocity we can detect is about 100 kilometers per hour, and the minimum is about 1 meter per second. The second principle that I want to show you is how we make the tracking of the rockfall. The tracking, as I told you before, is something that we perform not in real time, but after a few seconds. It's performed by the post-processing part. Every 0.5 seconds, the offline processing collects the position and the velocity of the moving target, and graphically are these circles that are the rocks at different time. It's the same rocks at different time. So every 0.5 second, the survey unit sends to the controller a sample with information about the velocity, the range, and the azimuth of the moving object. And the trajectory is simply the fit of the samples collected every 0.5 seconds. So just to give you a flavor on how we make the tracking part. Now let's have a look on the performance of the radar. We have a wide field of view that is 80 degrees in azimuth and 40 degrees in elevation. The operating range is configurable from us. It depends on what kind of scenario we are going to monitor. For landslide, for rockfalls, we have a maximum range of 2 kilometers. For the avalanche monitoring, we are right at 4 or 5 kilometers in range. The operating temperature is pretty wide too, for minus 40 to plus 55 degrees Celsius. We can supply the system both in AC and in DC. It's very important that to have a continuous power supply to the system, because as I told you before, the battery pack is just for backup, just to have a power for 2 hours after the main can shut down. The maximum Doppler velocity is around 27 meters per second. That is the 100 kilometers per hour. We have a double bandwidth due to certification, so we can operate both in US and Europe and in all the other countries. And 0.5 seconds is the Doppler integration time that I showed you before. So let's go through some key features of our software. The Rockspot system is operated by the controller software that is the one installed on the provided industrial computer inside the control unit. And the controller software is able to set up a monitoring session. And here the user has only to upload the digital terrain model of the scenario, and all the other configuration steps are guided by the software, and there is no need of particular knowledge of the system. I'll show you briefly later. The radar position is automatically georeferenced on the DTM thanks to the embedded GPS, and the user has to define graphically and drawing on the DTM the interested monitoring area, the alarm zone, and how he wants to be notified in case of an event on this area. And he can also draw an exclusion zone where he cannot want to receive alarms coming from moving objects, as for example, from cars traveling along a street, because our radar detects everything is moving in front of the radar, toward the radar. So it's very important to exclude all the parts that can bring false movement. In the next slides, I'm going to show you a typical wizard setup on the controller software. So as soon as the radar has been installed, as I told you before, the installation part takes about 20, 30 minutes. The user can configure the radar and configure the new monitoring section using the controller. So here we can insert the name of the session and go ahead. This is the first step of the wizard. The second step of the wizard is the view of the camera streaming. Since the field of view of the camera is pretty the same to the one of the radar, here the user can do some adjustment to the radar just to point on the right zone we want to monitor. After this step, we can also rename, of course, the sector name. And after this step, the software automatically look for the digital term model that the user could have previously uploaded, as in this case. And thanks to the embedded GPS, the DTM will be georeferenced, and the radar coverage will be shown projected on the DTM, is this in orange. The user now can draw the monitoring zone, and this is the last step of the wizard. So the yellow one is the monitoring zone, and then we can jump directly into the monitoring session. That's where the user can define the alarm and the exclusion zones. This part. In this tab, the user can define the alarm, the exclusion zone. The alarm zone is drawn, and then it is possible to define the level of the alarm and the criteria to trigger the alarm that is based on frequency. So how many events per unit of time. And here is the notification. We can be notified by pop-up, email, message, output port, and the activation can be manually or automatically after the event. We can also define the exclusion zones, like the streets, as I told you before. The exclusion zone are the gray polygon, and we can name them as the user prefers. Let's go through a typical monitoring session. We have the streaming of the camera. This panel is to control the temperature, the supply, the voltage of the system. We can also switch on and off the system with this switch. We have some graph just for troubleshooting part to see the supply, the power, and the temperature of the system. This is the part where you can see the coverage of the system, and you can adjust a little bit also the position of the radar. Here is the part that we see before with the alarm zone and the exclusion zone. And the last part, of course, here we can define the view from the radar, from the top, from the view from the graphical view. And this is the list of the geo events that the system has seen. And as you can see, all events have the information of the, sorry, it is a GIF, so it's repeated. All the information are enriched by velocity, area, and the trajectory. We'll see later also some events. So that software was the controller software that is running on board of the radar and is up to the configuration of the system and the alarm. The GeoCloud is the web application that collects in real time the information related to geo events detected by one or multiple rock spot systems. Sorry, I have to drink. GeoCloud makes the data accessible through the web portal. It could be on-premise or on cloud on the Amazon Web Services platform. It depends on the client preferences. The first key feature, it is a multi-user platform. So permits to manage multiple users with different rights of access. GeoCloud is also multi-site, so it means that a single GeoCloud instance can manage multiple Rockspot systems deployed in multiple sites. So from the same interface, the user can easily switch from one site to another. For example, if you have a company, your company have more than one Rockspot installations, you can control them from GeoCloud and switch from an installation to another, just clicking on site A, B, C, etc. Second key feature, the GeoCloud is also an event collectors managed by a database and can collect all the events detected by multiple Rockspot systems. Again, multiple systems all in one place. For each event, GeoCloud shows the trajectory, georeferenced, and overlaid on a geographic map of the monitored site. On the GeoEvent info, it is possible also to see additional information, such as from velocity, intensity map, and all the full list of GeoEvents can be filtered by site, Rockspot system, and date. The user can visualize and manage Rockspot and GeoCloud alarms, and GeoCloud shows and updates in real time the list of the active open alarms. So it gives the possibility to the user to manage them by adding comments, grilling them. It is also possible we can customize a bunch of things. Also, we can customize email alarms notification by adding a rule that is different dependent on the recipients. This is the site map. It is the most important page of the GeoCloud application. It is composed by this. This is a maps, the map section where there is the geographic map, where is reported the Rockspot system. The blue area, this one, are the monitoring area of the session. And on a GeoCloud can be present more than one monitoring area if in the selected time interval there are different sessions. The red one are the geo-event polygon that represent the area affected by the geo-event. Then there is the geo-event section. In this section, there is the list of all the geo-events registered in the selected time interval. There is the session section. In this section is present the list of all the monitoring sessions associated to the site and created in this time interval. And this is the time bar section. In this section, the user can select a specific time range by sliding the markers to filter all the site information, both in the graphical part and on the list part. So just to give you an idea on how the user interact with the Rockspot radar. Basically, he interacts with the Rockspot, with the radar by software. And so I wanted to present both just to give you an idea. So let's pass to the last part of the presentation. Here I'm going to show you some video of real use cases that we have collected during the last year of trials with Rockspot. As somebody of you may be known, the main business for IDS GeoRadar comes from monitoring radar for open pit mines applications. That's why I'll show you first 3 open pit mines installation, and then 2 use cases coming from the civil market. So this installation has been our very first installation in an open pit mine scenario. This is the visualization on the first release of GeoCloud. have to, sorry, I have to click play, but okay. So here you can see the rock that is falling on the right. On the left, we can see the intensity map of the event. Of course, the map is not rotated as the video. We are working on this. Just some words on this. This photo is taken from a geo server that is, I think in this case, Bing server. We have developed and we are going to release very soon is in 2 weeks, an additional feature. So we are going to be able to upload on the GeoCloud also customized orthophoto from the client, taken from drone or whatever, just to be more close to the reality, especially in the open pit mining when the activity are so active. So this is another example of another installation in an open pit mine in US. You see here there is the part of the rockfall, the trajectory, and on the left side there is the intensity map. Is a screenshot taken from GeoCloud. This is instead a video taken from the controller software. As you can see, the videos is pretty shaking because during this event there were a lot of wind. We saw that the wind does not affect the monitoring and the tracking. So we are able to filter out this movement by the processing part. And this is the last installation that I show you for the mining part. Is an installation in Finland. And it's dumping of a material, but it's pretty cool because we have seen also the bounce of the rock. And this is instead a very popular landslide in Italy. I'm pretty sure that you all know the Ruinon landslide. We installed the radar in 2020, and we have collected a lot of rockfalls from this installation. And we installed the radar during summer in 2019. And because the previous year, in 2018, 2 people were killed from a debris flow under this landslide. Sorry, not Ruinon, it's Valferré. Sorry, nobody has died in Ruinon, sorry. So this is an example just to show you the long run out of the rockfall. Maybe we can see again. I don't know if you have seen this. This is the interaction, the typical interaction in the controller part. So the rock was traveling from the middle of the landslide. And here I reported also a picture of the rock that is falling down, taken from a drone, just to give you an idea of the size of the rock. Here the range is about 600 meters, and for us 600 meters it's a very easy range. We can detect rock of 30-40 centimeters of diameters at this kind of range. And this is the same landslide in Ruinon with an event with a very short run out, just to give you the idea that we can track and detect both long run out and short run out. So this is the installation that I mismatched before. This is an installation in Val Ferré, in Valle d'Aosta, near the Mont Blanc. We installed the radar in 2019 during summer because the region decided to monitor this slope because in 2018, after an extreme rain event, debris flow killed some people, a couple of people. And so they decided to monitor the slope during summer. After the first month, they decided to leave the rock spot there, also to monitor the avalanche of from this part. So this has been our very first avalanche detected by rock spot radar. Of course, here it's pretty strange to see a different situation from the video, but it's the map from Bing with the trees and the greens. The video could give you just an example of what the radar is capable to do. It is very important to understand that the radar is capable to detect also during night, when it's dark, when it's cloudy, when there is fog, like in this situation. So I just want to show you this kind of event, just to show you this. And in the end, the last avalanches that we have detected 2 months ago in Val Ferré. The peculiarity of this avalanche was that it starts at 4.5 kilometers of range with respect to our radar. Of course, we detected it. We trigger alerts, pop-up, etc. And here I reported the trajectory. It seemed as if they were 2 branches of the avalanche. One that is these first branches, and the other one that goes down. So I finished this presentation with this spectacular image of the avalanche. That it's pretty cool to see this in front of a screen and not under the mountain. That's all. I don't know if with the time it's okay.